You must obviously take account of the forecast when planning a passage. Will there be too much wind for my and my crew's level of experience and the seaworthiness of our boat? Will it be a comfortable passage? How long will our passage take, considering the wind strength and direction? Is it safe to leave this harbour with the forecast wind strength and direction? Does our passage take us through any areas that might be especially uncomfortable or even dangerous with the forecast wind strength and direction? Will it be safe to enter our destination harbour with the forecast wind strength and direction? And how comfortable will it be when we're there? Is the forecast visibility sufficient for us to navigate safely, especially if we need to cross busy channels? Oh, and will it rain? And of course, all of the foregoing need to be considered not only for today's passage, but if we're planning 2 or more days' cruise, the entire duration of our voyage. Use the Resources tab to view the current Met Office inshore waters and shipping forecasts. You will see that in both cases, for all areas, the forecast is delivered in 4 parts: wind, sea state, weather, and visibility. At sea, wind strength is measured according to the Beaufort scale, and in knots, nautical miles per hour, or meters per second. The Beaufort scale was created by Rear Admiral Sir Francis Beaufort, an Irish hydrographer and officer in the Royal Navy. You can download and print this copy of the Beaufort scale and the table on the next page from the Resources tab. Wind direction is important because it dictates how fast we can sail in the direction we wish to proceed. If we imagine that it's the middle of a force 4, so a lovely sailing day, most modern 35-foot sailing yachts might expect to sail at around 6 knots upwind and perhaps 7 knots on a broad reach. So if you don't have to beat to windward and ignoring tide, you can make 7 knots in the direction you want to go, and a 10 miles passage will take 1 hour 25 minutes. However, if you have to beat to windward, your velocity made good, which is the speed at which you're actually progressing upwind, is unlikely to be more than 4 knots, so the same distance will take 2 hours 30 minutes. In areas like the Solent, tidal streams often run at 3 knots or more, so in lighter winds it might even be impossible to sail upwind against the tide. Remember, when describing the wind direction, it's the direction it's blowing from. If the wind direction changes in a clockwise direction, it is said to be veering. Whereas, if it changes direction anti-clockwise, it is said to be backing. And if it's said to be cyclonic, it probably means that the centre of a weather system is passing directly over the area, and the wind might change suddenly and unpredictably. Waves are the result of friction between wind and the surface of the sea. The factors that influence wave height are wind speed, the distance over which the wind has been blowing over the sea, this is called fetch. Hence, waves arriving on the west coast of Ireland can have a fetch of thousands of miles, whilst waves in a sheltered estuary will have a very short fetch. And the length of time for which the wind has been blowing from one direction. This is called duration. Swell is what we call waves generated a long way away, usually by high winds associated with gales or a storm. Wavelength is a function of the speed at which a wave is travelling. The faster the wave, the longer the wavelength. Far out to sea, waves might be large, but because they're travelling quite quickly, their wavelength is long, and your boat just goes gently up and down. For example, if the wavelength were 100 meters, you would go up, down, and back up again roughly every 10 seconds. However, if anything slows the waves down, their wavelength shortens. For example, if the wavelength shortened to 10 meters, you'd be going up and down and back up again roughly once every 3 seconds, and it would start to feel really uncomfortable. If waves are slowed down to the point where the wavelength is less than approximately 7 times the wave height, the waves will break. Any vessel caught beam on by a breaking wave more than 50% of her length overall has an 80% chance of capsize, and if the breaking wave exceeds that vessel's length overall, she will capsize. Waves are slowed down by a shelving bottom, underwater obstructions, or wind and tide or current in opposition. Other factors which can cause waves to break include any sudden change in wind direction, or local wind-generated waves moving in a different direction to swell. Breaking waves caused by any combination of a shelving bottom, underwater obstructions, or wind against tide are called overfalls. They are marked on large-scale charts and are usually described in the almanac. This is the Needles Channel at the western end of the Solent, where a ridge of underwater rock combines with strong tidal streams to create large, potentially dangerous breaking waves. This is the Needles Channel with a gale force 8 blowing against an ebb tide. This is the entrance to Chichester Harbour, near low water in strong wind against tide conditions. Notice the port hand channel mark right in the middle of the breaking waves. Here's a list of the descriptions used to describe sea state in terms of wave height. For each sea state, most waves will have heights within the range shown. However, larger waves can occur, although not very often. A useful estimate of the largest wave that you might see is 1.5 times the upper end of the height range. For example, for sea state rough, most waves will be in the range 2.5 to 4 meters. But if you're unlucky, you could encounter a wave of 1.5 times 4, which equals 6 meters. There's a complete list of all the terms used in weather forecasts available from the Resources tab. Weather is described in a more general narrative. For example, rain then showers, intermittent light rain, thundery showers, heavy rain, light snowfall, fair, fog patches, fog banks. Visibility is described like this: very poor, which means visibility less than 1,000 meters. Poor, which means visibility between 1,000 meters and 2 nautical miles. Moderate, which means visibility between 2 and 5 nautical miles. And good, which means visibility more than 5 nautical miles. You can download a summary of these terms from the Resources tab. There are many means by which you might obtain a weather forecast. These days, with an internet connection, forecasts are available from multiple sources, but we cannot rely on getting online when sailing, or even in many marinas or harbours. So we need to know what other channels we can use. These include the broadcast radio, our vessel's VHF transceiver, local harbourmaster and marina offices, phone and text messaging together with specialised radio transmissions such as Navtex and Weatherfax, and emailed GRIB files. If you do rely on a forecast posted up outside the harbourmaster's office, just check that it is today's. A very reliable means of obtaining the weather forecast on board a yacht in UK waters is to listen to the routine maritime safety information broadcast put out by the UK Coast Guard on VHF at 3 hourly intervals throughout the day. It is announced on Channel 16 and, until September 2017, will be broadcast on 23, 84 or 86. Thereafter they are moving to channels 62, 63 and 64. Depending upon where you are in the daily cycle, you will get more or less information updated or new forecasts according to whether the broadcast is routine A, B or C. Forecasts for UK coastal waters up to 12 miles offshore around the British Isles are divided into the 19 areas shown on this chart. They are issued as inshore waters forecasts 4 times a day and cover a period of 24 hours from 0000 hours, 0600, 1200 and 1800 UTC. You can access the current inshore waters forecast from the Resources tab. Strong coastal winds, which are force 6 or 7, are displayed in red for the first 24 hours of the inshore waters forecast. This example shows strong winds forecast for Shetland. The shipping forecast is broadcast on BBC Radio 4 and sometimes Radio 3 at 0048, 0520, 1201 and 1754. The bulletins consist of a gale warning summary, general synopsis, sea area forecasts and coastal station reports. In addition, gale warnings are broadcast at the first available programme break after receipt. If this does not coincide with a news bulletin, the warning will be repeated after the next news bulletin. On this chart there are gales forecast in the sea areas South Utsira, Fisher and Fitzroy. In addition, some bulletins include a forecast for all UK inshore waters. This can be heard on BBC Radio 4 at the end of programmes, approximately 0048, and on BBC Radio 3 at 0535, around the UK. In addition, gale warnings are broadcast at other times between programmes and after news. For example, that was the news, and now attention all shipping, especially in sea areas German Bight and Humber. The Met Office issued the following gale warning to shipping at 22:06 today. German Bight, west or northwest gale 8 to storm 10, expected imminent. Humber, west gale 8 or severe gale 9, expected soon. That completes the gale warning. When giving a gale warning, the Met Office will indicate a time interval for when they expect the gale to occur. Imminent means that a gale is expected within 6 hours. Expected soon, that a gale is expected within 6 to 12 hours, and later, in more than 12 hours' time. The UK Met Office also published an extended outlook for the next 7 days, broken down into 3 large areas. See the Resources tab. Navtex is a system of radio broadcasting weather, navigational warnings and details of distress situations, which are received, displayed and optionally printed on special purpose receivers. There are 2 frequencies and sets can be configured to receive one or the other or both. Broadcasts on 518 kHz are in the local language, those on 490 kHz are in English. In UK waters, 490 kHz is used to broadcast the inshore waters forecast. Here are some examples of Navtex forecasts. WeatherFax broadcasts on high-frequency radio can be received globally, either on special-purpose receivers with inbuilt printers, or via an HF receiver and a special-purpose radio modem onto a PC. There are many sources, most of which broadcast on multiple frequencies. Check almanacs for schedules. There are many internet sources of weather information, such as Windfinder and WindGuru. However, beware, as many are derived from the US Global Forecast System, GFS, or Weather Research and Forecast, WRF, weather models, because, like all US public sector data, and unlike UK Met Office data, it is copyright free, which means that it can be used to sell advertising. The problem is that these models are entirely a computer prediction, and haven't been moderated by experienced meteorologists. They also fail to take account of local topology. This often means that they forecast substantially less wind than the UK Met Office model. GRIB, gridded binary, files comprising highly compressed weather information can be scheduled for automatic delivery via email for reception either with a satellite phone or HF receiver, and then interpreted on a PC using special software to see forecast weather maps giving wind speed and direction, wave height and rainfall. They are available from a number of sources, but most commonly they are derived from the US Global Forecast System, so, especially in coastal waters, you should try to check them against a local source. So, there are all sorts of weather forecasts to choose from. The gold standard is the relevant National Meteorological Agency, for example, the UK Meteorological Office or the National Weather Service in the United States. Unfortunately, though, and especially in the UK, where the Met Office has been given a mandate to charge for its premium services, it can be difficult to get access to even medium-term weather forecasts. The shipping forecast only covers 24 hours, and the inshore waters forecast only extends to 48. True, the extended outlook takes you to 7 days, but the narrative covers areas extending to 250,000 square miles, so it's hardly useful in coastal waters. Surface pressure charts are more helpful, but you need a very good understanding of the development of weather systems and the movement of fronts to interpret them usefully. We'll come on to this later. So most people fall back onto forecasts derived from the GFS model, because they're readily available via the internet or at sea via GRIB files. These will take you a remarkably long way out. Your instructor has even seen them looking forward a month, which, given the instability of the Earth's atmosphere in mid-latitudes, is a complete joke. Nevertheless, if you're planning a week's cruise or an extended offshore passage, then you should consult as many sources as possible. Compare and contrast. You'll find a remarkable divergence of forecasts. The thing to remember, though, is that the further you look out into the future, the less confidence you can have in the forecast. By the way, these numbers, going from 90% down to 1%, are only an illustration. Just like everything else with weather forecast, degree of confidence depends on what's happening in the atmosphere and where you are. Clearly, there are places where you can be almost 100% confident, even for a period of months. The middle of the Sahara Desert being a great example. Even in the United Kingdom, there will be times when a high-pressure system lies stationary over northern Europe and Scandinavia, and nothing much changes for days. At the other end of the spectrum, with complex weather systems driven by a turbulent jet stream, liable to switch direction on a butterfly's fart, almost anything can happen. So, why do we have weather? After all, some parts of the world, such as the great deserts or rainforests, have pretty much the same weather conditions 365 days a year. Others have seasonal variation, hot and dry, hot and wet. Whereas the British Isles and South Island New Zealand, for example, have weather that often changes significantly on a day-to-day basis. Contrary to many people's belief, it's not because the British Isles and New Zealand are a small group of islands, or because they're on the edge of an ocean. After all, the Canaries are an even smaller group of islands, and their weather is very predictable. Spain is on the edge of the Atlantic Ocean, but its summers are reliably hot and dry. It's all down to the British Isles and New Zealand's positions relative to the equator. Radiation from the sun heats the surface of the Earth. Give or take approximately 23 degrees either way, summer, winter, this radiation hits the Earth perpendicular to the surface at the equator. Whereas at higher latitudes, closer to the poles, it hits the surface at an angle, which means the same amount of energy is dissipated over a larger area. It is also filtered through a greater distance of atmosphere. For these reasons, the Earth is hot near the equator and cold near the poles. When the sun's radiation hits the surface near the equator, it heats the atmosphere, which causes the air to expand and rise. This creates an area of relatively low pressure at the surface, which sucks air in, much like a bonfire. It takes moisture with it, forming clouds, and as the air cools, rain. Which is why the world's great tropical rainforests are concentrated around the equator. The air flows away from the center and sinks as it cools, creating areas of relatively high pressure at the surface. Notice that the surface winds blow from high pressure to low pressure, creating the world's great mid-latitude deserts. At a global level, some of this air flows back towards the equator, and some flows north, where it meets and rises above cold air flowing down from the poles. This creates an area of relatively low pressure at about 60 degrees north and south, and an area of relatively high pressure at the poles. These circulations in the atmosphere are called cells. Now watch this short video, sourced from YouTube, to see an explanation of the Coriolis effect, which plays a big part in the development of global weather systems. Amongst other phenomena, this results in the trade winds, which, together with the underlying ocean currents, create a conveyor belt for sailing ships which powered the economic development of Northern Europe. Even today, if a yacht wishes to sail efficiently and comfortably from the UK to the Caribbean and back, it will follow the trade wind route, south down the Portuguese coast and past the coast of northwest Africa as far as the Cape Verde Islands, before heading west. The return is via Bermuda and the North Atlantic. The point in the Earth's atmosphere, in each hemisphere, where the warm, moist air from lower latitudes meets and rises above the cold, dry air coming down from the poles, is called the polar front. It moves north-south with the seasons, but is generally located somewhere just north of the British Isles. Jet streams also occur at the junction of the cells. The ones at higher latitude, nearer the poles, are the most significant. High-altitude winds blow continuously from the west along these jet streams. Like any fluid flowing over an irregular surface, the jet streams which flow east across North America become turbulent before continuing onwards to Europe and North Africa. This turbulence causes them to meander north and south in fairly unpredictable patterns, with the amplitude and frequency of the oscillations becoming increasingly severe as they flow east. Sometimes the jet streams merge, at other times they are completely separate. You can go to the current jet stream forecast from the Resources tab. Remember, at the polar front, air masses coming from the southwest are rising up over cold air masses coming down from the northeast. Because the southwesterly winds are coming from over the ocean, they're carrying lots of moisture, whereas the northeasterly winds are dry. And, as always, when warm air rises over cold air, an area of relatively low pressure forms at the Earth's surface. The general direction of travel is west to east. So the leading edge of the warm air is called the warm front. And the leading edge of the cold air is called the cold front. In between the areas of low pressure are ridges of high pressure. Winds naturally blow from high to low pressure and are subject to the Coriolis effect, which means that in the northern hemisphere they are bent to the right. So in the northern hemisphere, winds circulate anti-clockwise around areas of low pressure and clockwise around areas of high pressure. You can see how they mesh into one another like gear wheels. In the southern hemisphere, it's the other way around. Ballott's law tells us that in the northern hemisphere, if you stand with your back to the wind, low pressure will be on your left-hand side. Here you can see a North Atlantic weather chart derived from a GRIB file showing adjacent areas of low and high pressure. The little fleshes indicate wind strength and direction. Think of them as darts. Each feather indicates 10 knots of wind, with half a feather indicating 5 knots. The colours are not that significant and simply relate to the approximate direction. Notice that the low and high pressure areas are surrounded by many approximately concentric circles. The lines making up these circles are called isobars and link points of equal surface pressure. In this example, the high pressure over the British Isles has a central pressure of 1034 millibars, MB. The low pressure to the west has a central pressure of 979 MB. You can see that a few hundred miles west of Ireland, the isobars are very close together, which means that surface pressure is falling rapidly as we move towards the centre of the low pressure. We call the rate change the pressure gradient, and wind strength is relative to pressure gradient. So, as here, where we have a steep pressure gradient, you can see we have very high winds, up to force 9. Notice that winds don't blow exactly parallel to the direction of the isobars, but are slightly backed. As a rule of thumb, they are backed 15 degrees over the sea and 30 degrees over the land. This is as a result of the Coriolis effect. In this example, as the wind blows offshore, it accelerates, making it more subject to the Coriolis effect, and bending it to the right. In this cross-section of a low-pressure weather system, you can see how the warm air mass climbs up and over the preceding cold, dry air mass. As it rises, it cools, forming cloud and eventually rain ahead of the warm front. At the same time, the following cold, dry air mass forces itself down underneath the warm air mass, forcing warm, moist air to rise rapidly ahead of it, resulting in heavy rain, squalls, and possibly thunder and lightning. The area between the fronts is called the warm sector. Pressure falls ahead of the warm front, remains steady or rises slowly in the warm sector, and rises rapidly on and after passage of the cold front. Which is why a barometer, or better still a barograph, is such a great tool for weather forecasting. A fall of more than 8 MB over 3 hours almost certainly means that there's a gale, force 8, coming, whatever the current wind strength. A fall of 5 MB means force 6, but if the wind is already force 7, then expect a gale within the hour, but if the wind is only force 3, you probably have 4 hours before the gale arrives. Notice that in the warm sector, the warm, moist air is in contact with the Earth's surface. So if the warm sector passes over sea, and the sea is relatively cold, it will cool the air. As air cools, it releases moisture, creating fog. This type of fog is called sea fog, or more properly, advection fog. In the British Isles, it is most likely to occur in spring and early summer, with a warm, moist southwesterly wind blowing over cold seas. Whereas on land, we tend to associate fog with calm conditions, normally in the late autumn and winter, sea fog can and does occur in strong winds or even gales, and doesn't burn off in the heat of the day, but persists for as long as the warm sector remains. Behind the cold front, the weather changes very rapidly. visibility increases dramatically, and persistent heavy rain gives way to isolated and possibly squally showers, which will gradually die out. The cold front moves faster than the warm front, gradually overtaking it, until eventually the cold front overtakes the warm front, driving cold air under warm, moist air, which then rises rapidly, causing heavy rain. This is called an occluded front, and is depicted on a weather chart as alternating semicircles and triangles. The point where the warm and cold fronts join to create the occluded front is called the point of occlusion. As you might imagine, the weather can be pretty foul here, with heavy rain and the wind coming from virtually any direction, shifting rapidly and unpredictably. In forecasts, these are described as cyclonic winds. So, if you hear this term used in a weather forecast, it means the point of occlusion, which corresponds to the centre of the low, is going to pass directly over the forecast area. The next sequence of slides describes the weather in the area of the red circle as a low-pressure weather system moves across it, travelling in a roughly northeasterly direction. Maybe 1,000 miles ahead of the warm front, we'll be enjoying glorious weather with clear skies and light winds from the east. The first signs that things are going to change will be the appearance of high cirrus clouds, a small fall in surface pressure, and maybe the wind starting to veer slowly. Gradually the clouds will thicken into altostratus, the wind will continue to veer, and the barometer keeps falling. Just ahead of the warm front, the wind might strengthen and back a little, as the barometer falls more quickly. Nimbostratus clouds bring rain and visibility deteriorates. Pressure continues to fall. On passage of the warm front, the wind will veer and increase. Once in the warm sector, visibility might be poor or fog with continuous light rain. The barometer, wind strength and direction will be relatively steady. Ahead of the cold front, also known as a squall line, there will be cumulonimbus clouds, strong winds, maybe violent gusts with sudden changes in direction, heavy rain or hail, possibly thunder and lightning. If you see a squall line approaching, you should prepare your vessel and crew. So reduce sail, close all hatches and secure lockers, stow all loose equipment, don foul weather gear, life jackets and harnesses, and switch on your navigation lights, and monitor VHF channel 16. On the passage of cold front, the wind veers and usually drops, but is still gusty. Rain lessens and becomes showery. Barometer rises quickly. Visibility suddenly improves. Behind the cold front, there will be small, fair weather, cumulus clouds, isolated, possibly squally showers, which will die out gradually. In reality, of course, it's a great deal more complex than has been described herein. Weather systems combine together to produce a complex spider's web of fronts and isobars. Nevertheless, you can now appreciate that the southern UK was taking one hell of a pounding at the time of this chart, with force 9 west-northwest gales and an approaching occluded front. The UK Met Office weather chart is issued along with the forecast charts out to 5 days ahead. These are updated every 12 hours around 0730 and 1930, with the exception of charts for days 4 and 5, which are only issued once per day at 1930. The reason that these two charts are only issued once a day is because that far ahead the forecast surface pressure pattern will change more significantly, due to uncertainty at this longer time period, and there is limited value in updating it every 12 hours. Charts are published online in colour and black and white. Note that only the black and white one carries the geostrophic scale. You can go to the current Met Office forecast weather charts from the Resources tab. Here's a chart for 1200 Friday the 21st of June 2013. You can see a weather system approaching the British Isles. To determine how fast it's moving, measure the distance between the isobars along the warm front. And lay this along the geostrophic scale in the top left-hand corner for the appropriate latitude, in this case approximately 53 degrees north. This gives approximately 40 knots. The warm front moves northeast at about 2/3 of this, which is 26 knots. The cold front moves at the full measured value of 40 knots. It will therefore pass right over the British Isles within the next 24 hours. In order to predict the wind strength, measure between the isobars perpendicular to the isobars. And again, lay this along the scale for the appropriate latitude. This gives what's known as the geostrophic wind speed, and is the wind's speed approximately 1,000 meters above the Earth's surface, where it is unimpeded by surface topography and friction. The surface wind speed will be approximately 2/3 of the geostrophic wind speed, so in this case 45 knots by 2/3 equals 30 knots, force 7. We know that in the northern hemisphere, winds circulate anti-clockwise around an area of low pressure, and the geostrophic wind will blow parallel to the isobars. However, because they're slowed by surface friction, they are less subject to Coriolis, so are backed 15 degrees to the direction of the isobars. We can also predict that the winds will be southwesterly and will veer westerly, then northwesterly later. Because the warm front, warm sector and cold front will all pass over, we can predict plenty of rain and possibly sea fog. Here's a satellite photograph of a weather system over northern Europe. You can see increasing levels of cloud ahead of the warm front depicted in red. Low cloud in the warm sector piling up ahead of the cold front in blue, and then rapidly dispersing behind the cold front. You can also see the point of occlusion, where the cloud is piled up the highest and the occluded front in purple. A very useful resource is the UK Met Office Real-Time Rainfall Radar, which can help you to judge the approximate position and speed of oncoming fronts. You can go to the current Met Office Rainfall Radar plot from the Resources tab. When the land warms up rapidly during the day, air rises over the land, creating a localized area of low pressure at the surface. It then blows out to sea, cools and sinks, creating an area of high pressure at the surface. Wind blows from high pressure to low pressure, creating a sea breeze. In order for the sea breeze to develop, the land needs to be more than 3 degrees warmer than the sea. Therefore, sea breezes are more common in the late spring and early summer than at other times of the year. In the British Isles, sea breezes rarely extend more than 6 miles offshore, but in other parts of the world, where large, very hot land masses are adjacent to cold oceans, they can extend up to 50 miles offshore. One sure sign of a developing sea breeze are small, fair-weather cumulus, fluffy white, clouds building over the land. When they start to blow out to sea, the sea breeze will establish itself very soon afterwards. Sea breezes are more likely when the gradient wind is blowing offshore, as opposed to an onshore gradient wind which can inhibit the upper level flow. For example, in the Western Solent and Christchurch Bay, the best sea breezes develop when there's a gentle northeasterly breeze blowing in the early morning. It's then not unusual to have a brief period of total calm before the sea breeze kicks in from the southwest, gradually building to force 4 or 5 before dying off in the early evening. At night, Rapidly cooling and therefore sinking air over the land can blow out to sea, creating a land breeze. In the late autumn and winter, the land breeze might carry land fog out to sea. Unlike sea fog, which is associated with the warm sector of a weather system and which might occur in association with strong winds, persisting as long as the weather system remains over the locality, land fog, which is blown out to sea, is associated with calm conditions and will rapidly burn off next morning. Did I just say land fog? We haven't covered that, have we? Actually, there are many types of fog. So far, we've only covered advection fog. Others include radiation fog, valley fog, upslope fog, evaporation fog, and freezing fog. There's a link under the Resources tab to an excellent resource from the UK Met Office which discusses all of them. Advection fog, which is also known as sea fog, or colloquially ha in eastern Scotland and eastern England, or fret in northeastern England, occurs when moist air passes over a cool surface until it can no longer hold its moisture and so forces it to condense, forming tiny particles of water which forms the fog. It typically occurs in spring and autumn when the warm sector of a weather system passes over a relatively cold sea, or in areas where there is either a continuous current of cold water meeting warmer, moister air from lower latitudes, such as off the Labrador coast, or where there's an uprising of cold water, such as offshore from San Francisco. Radiation fog usually occurs in the winter, aided by clear skies and calm conditions. The cooling of land overnight by thermal radiation cools the air close to the surface. This reduces the ability of the air to hold moisture, allowing condensation and fog to occur. Radiation fogs usually dissipate soon after sunrise as the ground warms. On mountainous coastlines, and particularly at high latitudes, rapidly cooling air can create violent offshore gusts, particularly in the late afternoon and early evening. These are known as katabatic winds. Watch out for stronger winds down valleys, between islands, around headlands, and along some shorelines. When there are mountains close to the sea, offshore winds can create an area of relatively high pressure on the windward side of the mountains, which can result in extremely strong offshore winds down valleys and along the coastline. For example, the Mistral off the southern coast of France. Earlier we said that winds were backed approximately 15 degrees to the geostrophic wind. Actually, that's at sea. Over land, they're even more slowed by friction, so less subject to Coriolis, meaning that they are backed by about 30 degrees. This leads to predictable wind shifts when winds blow offshore or onshore. Which means, for example, if you are sailing towards a shoreline in the northern hemisphere on starboard tack with an offshore wind, you will be headed. And to divergence and convergence zones. For example, in the northern hemisphere, if you are sailing in a channel, for example the Solent or the English Channel, and you have your back to the wind, there will be more wind on the starboard side of the channel and less wind on the port side. Winds blowing offshore can result in gusts or alternating bands of stronger and lighter winds. Thunderstorms are caused by instability in the atmosphere, with overheated air near the surface and cooler air above. This shows itself with towering cumulus clouds. As the clouds grow, a thunderstorm and/or a violent squall is possible. A squall is a short period of much stronger wind and heavy rain. Fortunately, they are much more common over land than sea, although they can drift over coastal waters. Thunderstorms can produce violent gusts, sometimes almost vertically down to the surface, and abrupt changes in wind direction. If you see one approaching, it is best to reduce sail, reef, before it arrives. Fortunately, it's rare for yachts to be struck by lightning, but if they are, most of the electrical and electronic systems on board will get fried. This has happened to your instructor. Some people advocate putting a handheld GPS in the oven, which might act as a Faraday cage. If you are beating to windward, always sail towards a predicted wind shift. In this example, 2 boats have set off at the same time, one on starboard tack, the other on port, making 5 knots. They have sailed for an hour, then the wind veered, shifted right, by 20 degrees. As a result of the shift, the boat which had set off on port tack towards the shift is 3 miles ahead after 2 hours. So, if you were planning a passage west down the Channel, let's say from the Solent to Falmouth, a distance of approximately 150 miles, and you knew that a weather system was passing over the British Isles during your passage, you would clearly plan to stay well to the north, blue track, as opposed to the south, red track. Also remember, from the lesson on tidal theory, that extreme high or low pressure can materially affect tidal heights which are based on the assumption that barometric pressure will be 1013 millibars. As a rough guide, a change of pressure of 1 millibar will result in a variation in sea level of 1 centimetre. Less depth for high pressure, more depth for low pressure. So for example, atmospheric pressure of 1030 millibars would lower the surface of the sea by about 17 centimetres, which could be significant.